Today I'm going to discuss about uh, challenges in the computing industry and then how to overcome these challenges. The computing industry where most of the AI or machine learning application or HPC or any graphics, you name any of the heavy math computing applications. These equations or applications are computed in a circuit which is taken care by computing these equations is that floating point unit. This floating point unit computes most of the heavy math. For example, on the left side you can see this is a deep neural network equation where they used to train neural networks. On the right hand side you can see this partial differential equation is for Reynolds Navier-Stokes modeling equations in HPC. And the bottom side you can see that this matrix is most frequently used in object transformations of any 3D object. So as you can see, these equations demand high power in terms of performance. So as a result, in order to meet the demand of these applications, there is always a trade-off. One has to pay for um, uh, or compromise certain things. So in order to meet the demand, most of the companies are fabricating their chip in a higher technology node. So once you fabricate the chip in higher technology node, what happens is that more and more transistors are going to sit in a die, and then it becomes a denser and denser. So since you're going to put more transistors in a die, the chip as a whole, it's going to be uh, uh, expensive. So you could see that uh, so the fundamental problem in the computing industry is that this is driving from how we compute, and uh, you could say that is there any way we can reduce the data path, or is there any way we can reduce the memory so that the power we can reduce the power consumption. In the meantime we deliver a performance. So that trade-off, we need to reduce this gap. So I would say that there is a way to do this, there is a way to reduce this trade-off. So there is a new number system called a POSIT, where most of the computation done, floating point computation done in a POSIT arithmetic way. So you could think of the POSIT arithmetic is an alternative to the floating point arithmetic. As you can see the graph on the top right side, so it can give you an overview or the glimpse of uh, between two number systems, POSIT and floats. So on the orange side, or let's say, sorry, the pink side, you can see the POSIT number system. So the POSIT gives you an extra edge because of you can see tapered. This is a tapered precision on the both the left and right side. This one right side and on the left side compared to the POSITs, compared to the floats. And the plot is drawn for the 32-bit. And similarly, you can see the plots for 8-bit arithmetic. So on the left side, you can see the graph for floats versus POSIT for 8 bits. So the most promising one is POSIT 8,0. You can see that POSIT 8,0 is more accurate than the float 8 bits. So here the POSIT 8,0 is that 8 bits with a 0 exponents. Similarly, floats here 8 bits with a 5 bits exponent. So you can see that if you compare floats with POSITs, you can see that it's almost about 3 times accurate results. Usually, in AI or machine learning applications, people usually look for around 3 decimal digits of accuracy. So the POSIT can deliver this accuracy. So in other words, POSIT is an efficient encoding for a number system. So if you could plot any closure plot for any basic arithmetic operations, for example, here I have drawn addition, multiplication, or reciprocal. So you can see that posits provide more promising computations. So in POSIT, we don't have an overflow or underflow or subnormal number, and there are no not much nans, and they are really closer to the real result. In other words, how closer to the uh, exact results you have. So you can see more than 70% of the results are exact. In other words, they are closer to um, um, real number. So you can see in the addition 75% inexact, in the sense how closer we are to the real answer, and 82%, about 82% in a multiplication, and similarly around 81% in a reciprocal. So if you think in terms of uh, the silicon and the performance for the POSIT units, is that so the POSIT unit is about 4 bits, little bit 4-bit increase in hardware compared to floating point hardware FPU, but the results are accurate up to double precision. So you have a huge gain here, and the power efficiency. If you compare the FPU double precision with the POSIT, um, it's not gonna draw so much power, because the silicon is less dense, and the performance, we could say it's going to be almost double the performance compared to double precision. So the throughput and the latency is much better. So if you try to think in terms of the bits versus the floating point bits versus POSIT, you could always see the half the data width. For example, 16 bits POSITs, 16 bits floating point accurate results are equivalent to 8-bit POSITs. Similarly, 32-bit POSITs are equivalent to half the 64 bits. So based on this POSIT, we have uh, 4 products in line. Falcon is suited for AI and machine learning. So this is a lightweight AI multi-core. So in this Falcon, we have 16 cores, and then this is suited for neural network training. TEDS is for automotive applications. So in automotive applications, a lot of the computations one has to do in a certain time frame. For example, injection or ignition timing, or vehicle dynamics, or brake assistance analysis. So this has to compute it in a certain period of time. So TEDS is suited for that, and we proudly say that we are the first one to provide C and C++ or Fortran compilers, native POSIT compiler. So yeah, so that is the TEDS product. And similarly, so we could proudly say that the Racer GPU, we are the first POSIT GPU in the world that it's just all of the computations in GPU in a native POSIT arithmetic and the POSIT computation manner. So in Racer, you could expect that most POSIT operations are calculated per watt. It can support all FP equivalent POSIT instructions. And the programming model of our Racer is similar to the CUDA. And Supersonic is best suited for HPC. This is in this Supersonic we have 64 cores, and then it can take a lot of complicated uh, computations. For example, it can support some trigonometric functions as well, and high-end mathematical functions. And it provides more accurate results than FA system, FP system. So, all of our products based on CFA technology. CFA stands for carry-free addition. So, in today's computation, as you might have heard about these buzzwords, AI, ML, or HPC, or graphics. So most of the computations are done, it involves addition. So the addition is a computation of two bit streams, and then so one has to compute 2 bits in a bit by bit. So when you go from least significant to most significant bit, so the addition is computed in sequentially. So the carry, when you add, we generate carry. So that carry has to propagate from LSB to MSB. So this is time consuming and power greedy as well. So because of this that the carry, so nowadays you can see a lot of the chips are fabricated in a higher technology node. That is to cope up with the performance and application demand. So the CFA is the technology. It won't propagate carry during the computation. In other words, all of the arithmetic computation done in parallel. So when it is done in parallel, so since it's not going to propagate, so there is no power consumption. In other words, the performance of arithmetic circuit will be higher. So, and moreover, the CFA technology is the arithmetic circuits becomes simpler. In other words, the silicon is going to be less denser, routing is going to be less denser, and then there is a once you increase, or once you do the computation in parallel, so you're going to reduce the dependency between each FP instruction. For example, an equation which is iterated maybe 1,000 times in a loop, so that equation is going to compute much faster way with the reduced dependency between instructions. So and the CFA technology, as I mentioned, it's not going to consume that much power. So, and then most of our customers say, okay, that is interesting, so it's okay, well then why we have your products? So most of the customers ask, what is the pain point? We don't see that pain point here. So we are happy with whatever the state of the art processor or FP systems we have. So so always it comes down to the cost of any chip. So this POSIT, the technology, our products, and it provides you less the cheaper. So since the data is going to reduce by half, so the silicon is going to be reduced to half, and the transistor going to sit inside, and a die is going to reduce to half. So if you look in terms of uh, the silicon and the bit width wise, you are going to save a lot of cost here. So once you reduce the cost, and the chip fabrication becomes cheaper. So the cheaper chip leads to higher profit margin. So usually, what happens nowadays, that you can see that any high-end electronic gadget, you name a laptop or a mobile phone, or any tablet. So you can see that most companies have high-end these products. So day by day, these getting faster and faster, but they are getting faster because they are fabricating the chip in a lower technology node. But I think the most companies tend to forget what customers thinking towards the price. So the price is, um, for any high-end digital gadget is going higher day by day or in a year by year. So, but I think this problem in a different way. So I would think in a way that, is there any way that uh, we can fabricate a chip in the same technology node, for example, 60 nanometer or 180 nanometer, and provide cheaper chips. So our products offer um, these benefits, and then they fill this gap perfectly. And uh, yeah, so I think, these are the benefits you could think of. So if you have any questions, please do get back to me through any social media channel, or you may visit our website, and you can contact us directly. Yeah, that's it. Thank you.